Hi everybody, this is Mr. Claus, and this is a quick tutorial about divergent boundaries and the seafloor spreading that happens at divergent boundaries. So what we have set up here, you can see this is kind of a model of what the mid-Atlantic ridge looks like. You can see the two plates moving apart from one another. That's going to make that a divergent boundary. Couple things to talk about. First of all, we know that this divergent boundary is happening because of the mantle convection occurring underneath it, where we have hot material becomes less dense, it rises up, it pushes out to the sides. That's what's pushing those plates along away from each other. That material then, the mantle then cools down, moves back, and we set up a mantle convection cell like this. So we're going to get rid of the mantle convection. What does happen here is that new crust is constantly being formed at the ridge. Some of that hot material reaches the surface, it solidifies, it becomes new crust. That new crust is going to push the old crust outwards. So it's not just that we have plates moving apart at a divergent boundary, we're actually creating new crust. Now the world doesn't get bigger making all this new crust because just as much as being created at divergent boundaries is being destroyed at a convergent boundary. Couple patterns we set up here. Towards the middle of the ridge are our youngest age rocks, and towards the outside, since those younger age rocks are pushing the older rocks outwards, 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 we get a pattern of the further we move away from the ridge, the older the rocks are. The same kind of thing happens with the heat of the rocks. The hottest rocks that are just formed, they're newly formed igneous rocks at the ridge, are there in the center, and then they cool down as they move outwards. Now there's an interesting thing that occurs when we create this new crust, and that interesting thing has to do with the magnetic minerals in those newly formed igneous rocks, obviously magnetite being the main one of those. When those rocks form, the magnetites within them align themselves facing north. Because they're magnetic, just like a compass points north, magnetic minerals are going to point north. We're going to say that in this model, magnetites, rocks that have magnetites that are facing north or aligned towards the north are in purple. Now the interesting thing that happens is occasionally the Earth's magnetic polarity flips, and things that normally point towards the North Pole are going to point towards the South Pole. I can change that by clicking right here. We're going to say that south-aligned minerals are going to be represented by this silver color, so I can have north-aligned minerals, south-aligned minerals, north-aligned, south-aligned. These magnetic pole reversals happen about once every 600,000 years on Earth on average. Now that is an average. I can have them happen once every million years or every couple thousand years. Scientists have no idea why that switch happens. But in normal conditions, what we call normal polarity, and again we're representing that with purple, the magnetic minerals when they form face northwards. Now what happens is over time, as I have these polarity flips, you can see a pattern on the ocean floor of north-facing minerals, south-facing, north-facing, south-facing, north-facing, south-facing. I'm going to pause it. So what you get is this symmetrical pattern moving away from the ridge. Now I need to stress that there are not actual colored stripes on the ocean floor. What these are stripes of north-aligned or south-aligned minerals. The minerals forming right now at the ridge in this model are south-aligned minerals. That means when they solidify as a rock, they are facing what on the Earth is south, because our magnetic poles have flipped. These north-facing minerals don't flip at this time because they're already frozen in place. This is really good evidence for plate tectonics. This is showing me that over time, these plates have moved away from each other at the exact same rate. Really good evidence that those things are actually moving. That's the only way I could get this symmetrical pattern of north-aligned and south-aligned minerals. Couple other interesting things. I'm going to play this again. If we have a long time between flips, such as for example, okay, we're making north-facing magnetites, north-facing minerals, and then south-facing minerals, south-facing minerals. A long time between flips ends up in very wide stripes like this. If I have a short time between flips, I have north-facing, south-facing, north-facing, south-facing, north-facing, south-facing, and you see that I get shorter, thinner stripes. So again, really great evidence that the plates are moving. Also good evidence of some of our Earth's history of how long we've been around and how the magnetic poles have flipped over time. Again, we have no idea why they have flipped. That's all. Try to remember your patterns of magnetic minerals on the seafloor that are great evidence of a divergent boundary. Thanks.